Now if we look at these two triangles again, the triangle of RI, RF and delta R, and the triangle of VI, VF and delta V, you can see that we have two triangles with the same with one angle equal here. Okay, is delta theta, here is delta theta, and with two sides equal. Okay, it means that this side RI and RF are equal, and when we look at this triangle, this side, the length of this side VI and VF are equal. The length of this side RI and RF are equal. So we can say that these two triangles are the similar triangle. Okay, this triangle and this triangle are similar triangle. So for two similar triangles, we will have that the size of delta V over V is equal to the size of delta R over R. Okay, this is the property of the similar triangle. Okay. That is, if you calculate the ratio of two sides, the length of two sides of two similar triangle, in this case is this side and this side, it must be equal. That is, the ratio of this side and this side must be equal to the ratio of the corresponding side, which is this side and this side. Okay, so if we write again that we have the delta V, the length of the difference of the velocity over V is equal to the delta R over R. You can see that in this equation, V is the length of, if we look at this figure again, you can use the length of this side, the length of this side or this side for V, and we can use the length of this side or this side for R, because the particle move in a uniform circular motion. So the distance or the length of the position vector from the center, which we use as the reference point, will be equal at any point on the path, and the speed is a constant. So the length of V here and the length of VI and VF are equal. So here we have that V is equal to the VI and is also equal to VF, and R is equal to RI and it's also equal to RF. Okay, if we rearrange this equation and divide it by the delta t, which is the time interval for the particle to move from point A to B, we will have delta V over delta t is equal to V over R of delta R over delta T. Okay, but if you look at this term, the magnitude of delta V over delta T is equal to the magnitude of the average acceleration, right? This term is equal to the magnitude of the average acceleration. So we have that the average acceleration of the motion under the uniform circular motion is equal to the V over R of delta R over delta T, the magnitude of delta R over delta T. You can also see that this delta R, the magnitude of delta R over delta T is also the magnitude of the average velocity. Okay, the magnitude of the average velocity. Now, if we take the limit delta t to approach 0, it means that the point B, the point A and B are very close. We will have that we take limit of delta t approach 0, and the limit of delta t approach 0 of V over R of delta R over delta t, it is equal to the V over R times the limit of delta t approach 0 of delta R over delta t. We can do this because, as we mentioned earlier, the speed of the particle is a constant, and the length of the position vector is a constant. So it's not depend on the time delta t here. So when we take the limit delta t approach 0, we can take this V and R out of the limit process here. And when you look at this term, the limit of delta t approach 0 of the magnitude of delta R over delta t, this term is nothing but the magnitude of the velocity, right? The magnitude of the velocity, and the magnitude of the velocity is the speed, right? So we can write this as V, which is the speed. We have discussed this before, that for the velocity, or instantaneous velocity, the magnitude of the velocity is the speed. Okay, so we have that this is equal to V. So finally, we have that limit delta t go to 0 of V avg, which equal to the magnitude of the acceleration is equal to the v square over r. Okay, it's equal to the v square over r. We give this a special name, AC, a special symbol, and we call this with a special name that is we call this the centripetal acceleration. Okay, this is a centripetal acceleration. The term centripetal means center seeking. Okay, the term centripetal means center seeking. So the centripetal acceleration means that the acceleration will point toward to the center. Okay, it point toward to the center. We can see this meaning clearly when if we look at this figure again. Okay, you can see that when we look at the change of the velocity here, the vi change to vf, and when we draw the change of the velocity delta v, you can see that this delta v point downward, and this is the direction of the center. Okay, you can see that here in this figure, in this figure for the position vector, you can see that the center is here, and delta v point downward. It means that point to the center. Okay, so that's why we say that the centripetal acceleration is center seeking, because it always points to the center of the circle. When describing the uniform circular motion, sometimes it is more convenient to use the period of the motion to describe the motion of the particle. And when we say period, it means that, or the definition of the period is that the period is the time to complete one revolution of the circular motion. So the total length of one revolution is 2 pi r, and the speed of the particle is v. From this we have that the period must equal to 2 pi r over v, and this gives us how fast the particle moves in a uniform circular motion.